All right, I'm excited to introduce our first speaker, Professor Yuval Rabani from Hebrew. Sorry, Professor Yuval Rabani from Hebrew University of Jerusalem. Professor Rabani has a long line of very influential work in discrete and combinatorial optimization, convex optimization, and so on. And without further ado, I'll let him talk about his work on online multi-server convex chasing and optimization. Professor
Thank
Rabani.
you. So let me see if I can repeat the previous success of sharing screen. Do you guys see the opening slide? Yes?
Yep,
Okay.
looks good.
So I'll talk about online multi-server convex chasing and optimization, and this is joint work with Sebastian Bubek and Mark Selke. Let me start by refreshing your memory about k-means clustering, or more generally, the class of center-based clustering objective functions. So we have as input a finite set X, a subset of a d-dimensional real space. And as output, we seek some sort of sketch of X that we will denote by, so the sketch will have length k. It will contain fewer points, C1, C2 through CK. These are points in RD that are supposed to represent X. And the quality of this representation will be measured by assigning each point in capital X to one of these sketch points or centers, C1 through CK. So we would obviously assign it to the closest CI. Every point X in the set capital X is assigned to the closest CI. And then we measure the Euclidean distance squared from X to CI. And we sum that up over all the points X in capital X, and that's the measure of the quality of our sketch. So this is at least one way of understanding k-means clustering. It's taking a large set of points and trying to sketch it into a small set of points where the sketch quality is measured by this squared Euclidean distance to the closest sketch point measure. Now, there's a very natural online version of this problem. And it goes as follows. So this is very natural because this is often how people actually have to cope with clustering problems. So the points in X are not known in advance. They are revealed gradually. They arrive in some online fashion. So we get to see X1, then we get to see X2, then we get to see X3. And we may also assume that this population, capital X, that we're trying to sketch may shift over time. So we're getting this endless stream of points, and there may be some meaningful clustering at some point in time, but when time progresses, the clustering may shift because the population changes, or depending on what these things actually represent, the segmentation of the population may change over time. So we can think of maintaining a set, a current sketch, a time t, we maintain a current sketch, C1t, C2t up to CKT. And this should predict the point xt. So we hope that our clustering is good, and it should be good on future points that we haven't seen yet. But we're also allowed to move our centers in reaction to the input that we see over time. And in order to capture both of these aspects of this setting, first of all, that we have a good prediction, and then so this would be the quality of our prediction, and then that if the clustering is meaningful, it can change very quickly over time. So we want it to be relatively stable. We're going to measure both things. So the quality will be the Euclidean, the squared Euclidean distance to the closest center of the point xt, and the stability will measure over time the movements that the centers do in Euclidean distance. So not in Euclidean square distance, but in a metric, in the Euclidean metric. Okay, so basically, our objective function in this online clustering problem will be to do well on the sum of these two measures, on the quality of the clustering and on plus the movement cost of the centers. There was a question?
Yeah, can I ask a quick question, please? Hi, I'm Yuval.
Yeah.
The question is whether you can choose this sketch based on the knowledge of xt, or you have to choose it without the knowledge of xt.
Okay, that's actually a very good question. So for now, we will be moving the centers, or at least the way I'm defining the problem right now, and we will actually change that soon, is that you first move the centers, you first adjust your clustering, and then you see what the, so you get to see xt. Now you can move your centers, and then you pay the cost of connecting xt to the nearest center. So you get to see xt before deciding on C1t through CKT.
And hence the stability measure is kind of neat, because otherwise there is no cost involved at all. Yeah. Okay.
Now we can talk about perhaps a different problem, but we'll see that these are related very closely, or we're actually seeing it now, and that's the problem of k-chasing of convex functions. So we can think of the previous problem, the online clustering problem, as follows. We're given a point x sub t, and this point defines a convex function. The convex function ft of x is given as follows. It's just x minus x sub t, Euclidean distance squared between x and xt. So this is a specific convex function whose minimum is actually x sub t. And we want to chase this convex function. Now, what does that mean? We have these, normally when you chase a convex function, you're moving one point. Here we have at our disposal k points, and in this case, there are 4 points, so k equals 4 in this example, and we're looking at a one-dimensional space, but in general it will be a d-dimensional space. And we're allowed to move these centers. We have to pay for the movement cost, but then we also have to pay for the service cost. And the service cost is just the minimum among all these chasers of the value of the convex function. So this part here will be the service cost of chasing chasing this particular convex function. So we get a sequence of these convex functions, and we chase them using k-chasers. And those of you who are familiar with online computing recognize this as just a merge of two well-known problems. One is the k-server problem. In the k-server problem, the function ft is 0 at xt and infinity everywhere else. So it's a limit of some convex function that increases very sharply when you move from xt. The problem of chasing convex bodies or convex functions, it's pretty much the same, where there's only one chaser and you get arbitrary convex functions. So both of these problems are well studied. And here is a very brief summary of what's known about them. They've been studied for a very long time. So the k-server problem was introduced, I think, in 1988 by Manasseh, McGew, and Slater. And just, I think, a couple of years ago, there were still many advances, in particular the papers of Bubik et al. And James Lee, that made very significant progress on the randomized version. So here, as I said, f of t is 0 at xt and infinity everywhere else. What's known is that for deterministic algorithms, the problem is almost completely solved. So there's a lower bound of k on the competitive ratio and an upper bound of 2k minus 1. In the randomized case, there's still some issues, but pretty much the lower bound is almost log k, and the upper bound is some polylog k and maybe some function of n, depending on which paper we're talking about. So this is the status of the k-server problem. The status of the convex body chasing problem. So convex bodies are just you have a convex body, and the function is 0 inside the body and infinity outside the body. But you can replace that with chasing convex functions. So when you have one server, so that's not a very big difference. This problem was also introduced many years ago by Fredman and Lineal, I think in 1989, perhaps. And here, when so I already explained the problem. There's a lower bound of square root of d and an upper bound of the minimum between d and square root of d log n. So that's pretty much what's known about this problem. And we're talking now about a problem that actually merges these two problems. And one of the issues is, of course, you can work in the configuration space. So you can think of your k-chasers as one point in the k-fold product of your space, but then you lose convexity. So one way to think about this problem is that we're trying to chase things which are not convex, but not completely removed from I mean, there's some underlying convexity. Okay, so let's start with the line. So we're talking about dimension 1. In dimension 1, it turns out that there's a very easy solution, a very well-known algorithm that works well for the k-server problem on the line, a deterministic algorithm. Some variant of that works well for chasing convex function, k-chasing of convex functions on the line. And this is double coverage. So what does double coverage do? This is sort of a generic situation. Here we have our servers or centers. C1 through C4. We get a new function f sub t. This is not a completely generic convex function because it's symmetric, but that's what that was what I could draw. So you could think of a more general thing where it's not symmetric. I noted here the minimum of where the minimum of ft is achieved, and what we do if this minimum is between 2 points, we move both of them towards the minimum until the until the movement cost of one of them is equal to the service cost. So they both move. The service cost is the minimum of the two service costs of each of these points. And we move until our movement cost is equal to the new service cost that we reached. And this simple algorithm, for the K server, it's K competitive. Here we pay an extra factor of 4, so one can easily show it's 4K competitive using essentially the same potential function that is used for the K server problem. Okay. So this is encouraging. So let's move on to dimension 2. In dimension 2, of course, due to the problem of one chasing of convex functions in any dimension, if k equals 1, there is a competitive algorithm. But here, unfortunately, if both the dimension and k are equal to 2, we're already in trouble. There is no competitive algorithm. And this follows from a very simple argument. First of all, it's easy to show that on the line, chasing the union of two segments, so if every request is, instead of a convex function, a convex body on the line is just a segment. So if we just have the union of two convex sets, two segments, each request is a union of two segments, and we want to chase that, there is no algorithm that gives bounded competitiveness. This is by reduction from the K. So you can mimic the K server on the line with this for any value of K. And because the competitive ratio depends on K, as K grows, you get unbounded competitiveness. Now here in 2 dimensions with convex sets, we can emulate this by replacing each request in the two segments, in the union of two segments on the line. So we have a request that is the union of two segments, A1, A2, and B1, B2. We can replace this by repeating 4 requests to 4 convex sets. So the convex sets are the red segment on the top, the green segment on the top, on the bottom, and these 2 yellow and blue convex sets that span between the 2 lines. If you repeat these many times, then the only possible solution for the algorithm not to keep paying high cost is, first of all, to place one server on the red line and one server on the green line, and also to place both of these servers in the same segment on the top and the bottom. So either in the segment A1, A2, or in the segment B1, B2. Any other solution would keep incurring some cost. So the algorithm, since the algorithm knows we're going to repeat this many times, it moves to this configuration, and this mimics the chasing of 2 segments on the line. So no bounded competitiveness for chasing convex functions in general. But k-means is a specific convex function. It's not a generic convex function. So maybe the idea of chasing a generic convex function failed. Maybe we can chase k-means. And it turns out that we can solve the online k-means problem despite not being able to chase convex sets in general. And the idea is as follows. So we're going to replace our objective function with a different objective function. So instead of f sub t, which is the convex function derived from the k-means objective, we're going to use this ft tilde. And ft tilde is proportional to the Euclidean distance to xt rather than the squared Euclidean distance. But the factor of proportionality depends on the location of our servers. So ct minus 1 min is the closest center to xt before we move. So we're going to use this ft tilde. And this reduces the k-means objective function to some k-median objective function, where you're looking at Euclidean distances instead of squared Euclidean distances. And the functions are of the form some factor alpha t times the Euclidean distance, with alpha t being greater than 0. Now we're also going to consider only algorithms that we call move to minimum. Algorithms that we call move to minimum algorithms, they either move to the point minimizing f sub t, or they don't move at all. Okay, so these are basically the two ideas behind the algorithm, and here is an illustration of this change in potential function. So instead of ft, which is the k-means objective in red here, we're looking at the green objective. I'm drawing this on the line, but you should think about this as being in higher dimensional space. So we're looking at this green objective. And for the closest center, the red and green objectives are equal, but otherwise they differ. So the green objective underestimates the cost beyond the minimum and overestimates it when you're closer to xt. And really the problem here is when the adversary that we're competing against is closer to xt than we are, because then we're overestimating the cost of the algorithm. Okay, so the actual argument goes through a whole sequence of reductions. So we start with online k-means. Now we want to we want to change the objective of k-means a little bit by scaling it. So we repeat mt times the function squared Euclidean distance divided by mt. So some other convex function. And mt is chosen so that at the places that we are, the k-means objective is smaller than the Euclidean distance. So we choose mt to be big enough, and we get the sequence of requests. Now we switch to move to minimum k chasing of these convex functions, but not just to move to minimum, to blind move to minimum. What does blind mean? Blind means that we first pay the service cost and then we move. So is it Chaba who asked the question in the beginning?
Yep.
Yes. So we're actually now changing the game and paying the service cost before we see the convex function. And turns out that because of the change we made in the previous step, this doesn't matter by more than a constant factor. Now, the next step is to switch from ft to f tilde t, but this would give us also alpha t less than 1. So alpha t was bigger than 0. It's also less than 1. And now that we have this blind move to minimum online k median problem with alpha t less than 1, this is easily reducible to the k server problem by simply not doing anything with probability 1 minus alpha t and feeding the request, the current request, to the k server algorithm with probability alpha t. So here we pay also a constant factor. And the only difficult the only difficult step in this reduction is moving from chasing convex functions ft to chasing convex functions f tilde t. And this costs us an extra factor of k in the competitive ratio. So we will get a competitive we will get an order k squared competitive algorithm given an order k competitive algorithm for the k server problem. The argument, let me go back here. So just in one sentence, the argument is that the adversary can't be too close to xt too often, in the sense that most of its cost is when its distance from xt is not much closer than we are. And that's thanks to the competitiveness of the k median of the online k median algorithm that uses the k server algorithm. So this is, in very briefly and without going into details, the crux of the argument. Okay, I have to just okay. So this sort of sums up the technical part. I just want to mention that the paper has more results. So first of all, the reduction that I showed applies not only to the k-means objective, but to a class of well-sharpened functions that includes also functions that are not convex. So we can't k-chase all convex functions, but we can chase a nice class of functions, well-sharpened functions. The argument gives an order k competitive online k median algorithm. I briefly mentioned that. And the other points are about, I have to explain a little bit. So far this talk was about the competitive analysis genre of online computing. There is a completely different genre of online computing called regret minimization that is popular in online machine learning and online learning. In regret minimization, we have to assume something about the function. So, for instance, that they're one Lipschitz on the unit ball. And we also, in regret minimization, you normally don't pay for the movement cost. So we study this issue of k k chasing, or in this case k action regret minimization as well, and there are some. We have some interesting findings that are summed up here. So it turns out that in general, if you look at t steps of chasing, so the idea is that you have k chasers or k actions, and you pay the minimum of these k actions. So we get regret that depends on the dimension. For arbitrary one Lipschitz functions, we know how to get rid of that for linear loss functions, but not in general. And that's one of the open questions here. Does it depend on the?
No, in the room.
I'm sorry.
Could you repeat that?
Yeah.
Sorry, that may be background noise from my side. Sorry.
Oh, okay. Sorry, there was some noise. Anyway, so I guess the obvious open questions here are: is this D here necessary? Dependence on the dimension, but by the way, the algorithm here is inefficient, and that's inherent. So getting sublinear regret would require is NP hard, and I'm done basically.
Thank you, Yuval. I think we can have like one question or two questions if there are some quick ones, but if there are longer discussion questions, let's reserve them for the discussion period. And meanwhile, can the next speaker, Stefan, set up, please?
So I need to stop sharing, right?
Yeah, yes, thank you.
You have a simple question. There is a classic Lloyd's algorithm, right? In this clustering, which is an incremental algorithm. It updates the nearest center and moves towards the new point. Is that a trivially bad algorithm for the setting you considered?
I'm sorry, I didn't understand the question.
Oh, there is this. My computer is still playing up. I would just like, it's a naive question. Okay, never thought about these problems too much. So the naive question is that there is the classic Lloyd's algorithm for K-means cluster.
Yeah, okay. Yes.
So what do we know about Lloyd's algorithm for these settings?
Okay, that's so you get a new point, and what do? You do one round of Lloyd with
something like that.
Nothing. We don't know much or anything about it. But Lloyd could be really bad, even if you know all the points in advance.
Okay.
Right. Maybe on that note, like let's discuss that in the discussion period, and let's move on to the next talk. Yeah.